Hello friends, and today we will see some PYQs of coordination chemistry. So first is our PYQ from NET exam 2019. Okay, so over here we have in the electronic spectrum of I, Br6 2 minus, the number of charge transfer bands and the origin are respectively. So first of all, when we see for I, Br6 2 minus, okay, so this is iridium and so over here it clearly says that it is charge transfer, not the normal DD transitions, right? So the origin are, so we know as a fact when over here this is 4 plus, right? IR is 4 plus, this is 6 minus, so the overall is 2 minus, right? So because this is 4 plus and because Br is a like a electron donor ligand, right? So we can say that over here we get LMCT, and in LMCT we know it as a fact that ligand to metal first, this is right, that there are two charge transfer bands that we get, and one is sigma to T2G and one is sigma to EG. Okay, so this is a fact. Okay, and so there's a big derivation for this. I'm not going into that. So we are just looking at questions and how to solve them. Right. So correct order of molar extinction coefficient or values of the visible absorption band in the following species is. Okay, so first of all, molar extinction coefficient. Okay, that is epsilon. So epsilon is high when there's an intense color, or the color is intense, right? Intensities of color is high, right? So over here, what do we have? So we have NiCl4 2 minus, Cr H2O whole 6 2 plus, and MnH2 whole 6 2 plus. Okay, and chlorophyll is there. So it's a fact that chlorophyll has a very intense color. Okay, the chlorophyll pigment that is there, magnesium complex, it has a very intense color. So even if you don't know the fact, even if you just know the other three facts, so say let's see over here other three facts, and how can we say? So first it is NiCl4 2 minus, right? So this is a tetrahedral compound. A tetrahedral compound, so it is, so over here for intensity of color we see for two rules. One is Laporte, one is your spin selection, right? Laporte is for centrosymmetric molecule, centrosymmetric, right? So a tetrahedral molecule is not centrosymmetric, so it is Laporte allowed. It is as well as spin allowed, so it is very much allowed, and because it's very much allowed, the intensity of the color is high. Intensity is high. But over here for CrH2 whole 6 2 plus, okay, this is spin allowed, but it is Laporte forbidden. So it's Laporte forbidden, so it the color is a bit pale, right? Not that intense. And for over here we have MnH2 whole 6 2 plus, right? So over here Mn2 plus, which is a D5. So D5 is the only like configuration of D electronic configuration which is spin forbidden. So this is both spin forbidden and Laporte forbidden, so it will have the least color. So from this logic we can say that this is the answer. So next question from GATE. The del zero value of Ni, this Ni complex, nickel complex of nickel aqua complex is at 8500 centimeter inverse. The del zero values of NiCl6 4 minus, NiNH3 whole 6 2 plus compared to this are. So we're going to compare this value with the values of NiCl6 4 minus and NH3 whole 6 2 plus, right? So let us compare and see what's going to happen. Okay, so first of all, uh, we can say that this is an aqua complex, this is a chlorine complex, and this is a ammonium complex, and we know, so over here all of them have, if you see, all of them have the same electronic configuration, that is Ni2 plus, right? This is 4, this is 6 minus, this is 2 plus, overall is 4 minus. So what is different? The ligand. And we know from the spectrochemical series of ligands, like which is strong and which is weak. And we can say that chlorine comes here, and then we have water, and then we have ammonia. So this is the line of strong ligands, like the strength of them increases, and the strength increases, the del zero value also increases, right? So the del zero value of NiCl6 4 minus compared to water will be lower, and NiNH3O6 2 plus compared to water will be higher. So the B is the answer. Next question. From GATE 2018, the lowest energy DT transition of the complexes follow the order. So we have chromium complexes, and over here we have three different like ligands. One is aqua, one is ammonia, one is the cyanide one, and we already know from the, as I showed you, you can follow the simple rule of X, O, N, C, where X is a halogen, O is oxygen, and N is nitrogen, C is carbon. So an aqua complex, the strength is lower than nitrogen than a carbon, and therefore the del zero value is also the same for the same order, right? And in GATE 2017, we have this three complexes, and this exhibit intense ligand to metal charge transfer transitions. So one thing we should know that for LMCT and for both LMCT and MLCT, the configuration has to be like D0, right? Normally the configuration is D0. So if we see over here, so this is MnO4 minus. The whole charge of this complex is just -1. So O4 is actually -8 because oxygen has -2 charge and 4 of them, so it's -8. So this has to be +7. And we know that Mn plus 7 is actually D0. So, and if you see for all these also, you will see that it is like a D0. So if we see for this, like we can say this is like -8. So this has to be like plus 5 to make it -3. This has to be +6. Okay, so these are like D0 complexes, right? And so V plus 5 and Cr plus 6 are like D0 complexes. So the wavelength we have to compare, okay, of the intensity. So normally we know, so we have to compare the wavelengths. So normally we know that when the metal has a high oxidation state, it is like very facile charge transfer, very facile CT. So the energy can be said to be lower, and because the energy is lower, the wavelength is high. So the wavelength will be higher for high oxidation state. So highest will be for MnO4 minus, then for, okay, so I think there is a small mistake over here. Just check it. So there's a like small note over here that MnO4 minus has the highest oxygen state, and thus LMCT is most facile, and thus has the lowest energy, and thus the highest wavelength. That's what I exactly said, right? Lowest energy and highest wavelength. So there's a small mistake as I can see in this. So the right answer that will be is actually C, not A. It's not A, it's actually C, because CR actually has +6 and B has +5. Okay, so higher the oxidation state, the easier it will be, and then lower the energy and higher the wavelength, right? And this from GATE 2016, we have that in first row high spin transition metal complexes MH2O6Cl2 with D5 and D7 metal ions, the DT transitions are. So we already said that D5 is like spin forbidden. Okay, it's a fact that D7, it's like there's a, if you just see that the spin selection rule, which has to have like del S equals to 0, right? It will be spin forbidden, and D7, which we have, will be spin allowed. So this is the answer, like D5 is spin forbidden, D7 is spin allowed. Okay, and so the next one, the intense red color of Fe bipiridine 3 whole 2 plus is due to what reason? Okay, so over here we can say that like so there can be like LMCT and MLCT, right? For these, so for LMCT normally the ligand to metal that is there, the ligands has to be like a donor ligand, like a pi donor or sigma donor, and for MLCT the ligands has to be like pi acidic. and over here also bipiridine is actually pi acidic. Okay, and therefore, and over here we can see the oxidation state is also not that much. It's just okay. Sorry for that. Yeah, so it is just +2 over here, right? So it's not that much. So it cannot be LMCT, right? And it's neither like DD transition because there's an intense red color. For DD transition, we don't get intense colors. It's only for LMCT and MLCT, and also for like a pi star that we have, or intervalence charge transfer. But there's no case of intervalence over here, so we can eliminate these three. So the only one left is MLCT, right? Metal to ligand. Another gate question over here: the increasing order of wavelength of absorption for the complex ions. Okay, increasing order of wavelength of absorption, right? So we have some like complexes. One is, so this is the simple one, as I said, it's XONC. You just apply this simple formula. So it's saying like the wavelength. So this is actually for the energy, the wavelength will be opposite. Okay, so this will be the lowest, then it will be the ammonia one, right? Then the aqua one, and then the X one. So that's it. And the next one, isoelectronic series of this VO4 3 minus, CO4 2 minus, MnO4 minus, all members have intense charge transfer bands. Incorrect statement is charge transitions attributed to excitations of electrons from ligand to metal. So they are saying it has to be from L to M. But okay, the charge. So that's right, actually, right? Because as we have discussed before only, that all these actually have high oxidation states, and because these have high oxidation states, the and these are actually donor ligands, so it will be actually ligand to metal. Okay, so let's see the next question. MnO4 minus exhibits charge transfer as shortest wavelength among these. So we already discussed that this is the most facile. Most facile means energy is lowest and the lambda is the highest. So it's not the shortest, it's the longest wavelength, right? The wavelength of transition series follows the order. This is actually a true statement. We actually just saw this in the previous question itself. The charge on metal nucleus increases in the order like this. And we also had a doubt whether the previous question we discussed, there was actually the wrong answer given, right? We just discussed in this that the wrong answer given, but this we said is the right answer. Now we can actually verify from this question itself that these are the right sequence. So this is actually a trick in exams. When you don't know something, just skip it, and you might actually find some hints of that question in some other related question. Might be. The dark purple color of KMNO4 is due to charge transfer. So it's whenever it's dark, it has to be charge transfer, right? Not DE transition. And these are like these things, ligand field transition and sigma pi transition. We actually have not learned all these things. So just remember that for Ruby and we actually have this pi to pi star transition. But these things actually we don't have, so you can just skip that. So actually previous year questions, like 2003, so they might have asked in those times. The lowest energy DT transition in the CR3 complexes varies in the order. So lowest energy. So again, this is the same XONC formula you have to apply and you have to do that. So I'm not going into the details of that. Amongst the following, the strongest oxidizing anion is the strongest oxidizing anion. Okay, so it's an oxidizing anion. It means that it can oxidize others and itself it will get reduced, right? And if itself it gets reduced, it means it shows your LMCT, ligand to metal charge transfers, very easily because it's donating very easily. So it like okay, oxidizing anion. Okay, when it is actually okay, sorry for that. So it actually will be MLCT, not LMCT, because oxidizing as in the sense like it's oxidizing other things. So it itself gets your reduced. So it will actually like want to like accept electrons. So if there is some possibility of MLCT, it will be good. And for MLCT, so as we can see, we can actually just see the your what you say the charge of the metals. So over here MnO4 2 minus, this is actually like 2 minus is -8, so this will actually like have uh, your +6. charge. Fe will also have plus 6 charge. V will have your plus 5 charge, and Cr will also have plus 6 charge. Okay, so over here it says the strongest oxidizing anion, right? So because it has like a plus 6 charge, and like Fe in the plus 6 charge, there is how many electrons in Fe? We can say that there is like plus 3 plus 4 plus 5 plus 6. So there are like 2 electrons in Fe. In Mn there is 1 electron. I think there are 0 electrons over here, 0 electrons over here. So because this has 2 electrons over here, it can easily like okay, so that's facing anion. It has 2 electrons. So okay, so just skip this question for some time. Okay, I'm not actually getting the answer to this. Just skip this question. I'll maybe come back later in the comment section. So the thing actually is this has 2 electrons, so it can actually donate electrons easily, right? If it can donate electrons easily, then it has to like better than others, right? So it should be strongest reducing anion because it's donating electrons because it has more electrons. But oxidizing means that it oxidizes others and accepts electrons. Hmm. Okay, so just wait for some time. Maybe later we'll see to this. Okay, the orange color of Cr2O72 minus is due to. Okay, so again we see this is like a donor ligand, and this also has a like very high positive charge of plus. It's around like it's very high, right? Maybe plus 6, I think, right? So it has to be ligand to metal, right? So next one, the oxidizing power of Cr4 2 minus, MnO4 2 minus, and FeO4 2 minus. Okay, the same thing we have discussed, and now actually we have a reason written over here. So good only, we will see the answer to this question. Okay, as the oxidizing property decreases down the group, it should increase across the period. As the atomic radius also decreases across the period, ZEF increases. Therefore, it can take electron easily and thus oxidize others easily. Okay, cool. So normally we know a trend that something that decreases down the group, right? It actually increases across the period, and the vice versa, right? If it like increases down the group, so it will decrease down the across the period. Okay, and so we know as a fact that oxidizing power like decreases down the group, so it should increase across the period. And the reason given over here it is because the charge like the radius actually decreases across the period. So if the radius is actually decreasing across the period, right, the Z effective actually increases, right, because the radius is small. So the like what do you say, the effective potential that's from the nucleus to the outermost shell, because the size gets small, it's actually the potential gets high from the nucleus to outermost shell, the effect of the Z effective gets more. And because this actually happens, so it can actually accept electrons more because it's actually the charge may be the same, like +6 for everyone, but because Z effective is more, it can actually accept electrons very easily, right? So that's why FeO42 minus has the highest than MnO42 minus, because it's going across the speed and the charge and the radius it decreases across this, because of which the Z effective increases across it. And all of these three have the same charge, that is +6. So we actually have to use this Z effective concept to solve this, right? So that actually makes sense because the charge increases, therefore the ability to accept electrons also increases, oxidizing other things. Similarly, among the following, the strongest oxidizing agent is, okay, so we just said like the oxidizing power, it decreases like down the period, right? And we know like MORE, they're all in the like uh, below periods than CR. CR comes like in the 3D, right? This comes in 4D. Because this is above, this has actually more oxidizing power, and we can actually again use this concept of R, because R is actually less for a 3D than a 4D, right? Because the shells actually are less, so that is the most obvious reason. And because R is less, the Z effective is more, and all of these again they have the same charge, so we actually have to use this concept of Z effective, because Z effective is more, it can actually accept electrons very easily because of the plus and minus, right, concept, and because it can accept electrons easily, it can oxidize others easily. So that's the reason. Okay, so I hope this concept is very clear. I took some time, sorry for that, but now I hope it's clear. Okay, for electronic spectra of K2Cr2O4, K2MoO4, the correct combination is, okay, so electronic, so the answer is not given over here actually. I think there was some discrepancy in this question, that's why. So we'll just leave this thing, or we can just see the approach of how this is done, like CR and MO. So both of these are actually in the, so as we know, so they are actually in the like 3D and 4D, right? And we know it as again as a fact that this has to be like LMCT, because oxygen is actually a like donor ligand, and because it's a neutral compound and this is like +2, so this actually has to be like +6 for both of these, right? +6 for both of these, so this has to be like LMCT. So we can actually cancel these two options very easily, and we can just have to compare the lambda max. So we just see the procedure of how it's done, right? So uh, yeah, so the charge is the same. So again, we can actually use this concept of oxidizing power, or which is easy. So we actually know that this oxidizing power of Cr is more because of the, it comes in the 3D and this comes in the 4D. And because the oxidizing power of Cr is more, so what we can say is that it can actually accept electrons more easily, right? And because it can accept electrons more easily, the energy should be lower, for which the lambda should be more. Actually, the lambda should for A should be more. So I am going for this answer number 3, right? It can actually be solved in other techniques as well, but some concept that makes sense, I believe, that answers, right? And over here we have CDS, HGS, and B bismuth I3. Okay, so bismuth compound, and is color due to. Okay, so so see, DD is actually not the reason. Okay, so DD is does not actually give strong color, so we can cancel this out. And combination of LM and DD, this also can cancel out, right? So it's basically up to your L2M or M2L, right? And we know that oxygen and sulfur, both of them are like they can donate, as well as the halogen ones. So it's actually a ligand to metal transfer, right? Okay. So the next question we have COL6 3. Okay, this should be, I think, 3 minus. Is red in color, whereas COL6 3 plus. Okay, okay, so it is 3 plus, I believe. Is green. Uh, L and L plus respectively corresponds to. So this is actually 3 plus. Okay, this is actually red, and this is green. Okay, so red in color, that means that it absorbs green. So if it absorbs green color, it will show red in color. So like the lambda, so as we know it, like wave gear, it actually goes from like wave. Okay, like, let me draw a bigger picture over here. So if we, the color chart I'm drawing, okay, it's a rough color chart. So like 400, it starts from 400 nanometers to 700 nanometers, right? So like in this way, we can say like wave gear. So we can say green is over here, Y, orange, red. So red and green are actually opposite to each other, right? So what we can say like COL6 3 minus is red in color, so it absorbs green color, so it's absorbing in this area, right? It's absorbing in a lower wavelength, so it's absorbing a lower wavelength. Okay, that means the energy of transition is high, right? And because the energy transition is high, that means this actually has to be a strong ligand, and so it cannot be, so this actually respectively, so it's given respectively in the sense like in the same order, so it cannot be, so the first one has to be a strong ligand, right? So it cannot be H2 and NH3 because first one is weak ligand, or it cannot be NH3 and 110 phenanthroline because first one is a strong ligand. So it can be this or this, and it's saying that NH3 is red in color and this is like green in color. Okay, so actually there's not much of a difference between NH3 and 110 phenanthroline as there is an NH3 and H2O. And because it's red and green are two opposite ends, so it has to be like NH3 and H2O, right? So the same thing we can say for green. It is a green in color, so it absorbs like the region in red. So the lambda is actually high. The energy of transition is low. The energy transition is low. That means there's a weak ligand involved, which is H2O. Okay. So now we see the next question. The light pink color of COH2 whole 6 2 plus and the deep blue color of COCl4 2 minus are due to light pink and deep blue. Okay, so light pink actually can be due to DD transitions, and over here it's saying that deep blue is also due to DD transitions. Okay, so one reason we can say that see, because LMCT and MLCT doesn't really give light color, it actually gives a very dark color, so we can actually eliminate these two where it says in the first or in both. Okay, and this actually could have been a case of like DD transition in first and MLCT in the second, but over like CO2 plus is actually not in the your D0 transition state as we said before. And this is an important thing to note is also this is actually a tetrahedral compound, unlike the octahedral compounds which is Laporte forbidden, and some of them are spin forbidden as well, but the tetrahedral compound is not Laporte forbidden, so it actually can show a dark color without being LMCT or MLCT. It can be a D transition as well, right? Okay, so match the items in the three columns, and okay, so let's just see how many questions are left. Okay, okay, let us do this question. NiH2 whole 6, NiNH3, this part is same nitrate, NiN. So we know like which is strong, which is weak. So H2 is weak, NH3 is stronger, En is stronger than that as well. Okay. Okay, the absorption and color. So this is strong. So this actually should have a like lower absorption wavelength, right? So we can say, and lower absorption wavelength means from the color chart we can say that if it absorbs a lower color, it will show a, like a lower wavelength, it should show a deep color, right? So for En should have the lowest, uh, this 565 should be for En, and it should show a deep color on which is, or the like Vibgyor should not like deep, we should actually go in this place only. So violet, green, blue. Okay, so I believe, okay, so I believe the color they are showing over here is that actually more than 500. Okay, okay, 565. So actually this starts from 400, this ends in 700. 565 is somewhere around here, right? 565. So it actually corresponds to violet. So this has to be violet, and this is 565. So we got one C3Y, C3Y. So over here we have one C3Y, one over here we have C3Y. But this is a technique to know that you are going the right direction, right? Because both options have the same uh, sequence. Like both have, options have the C3Y, so you are know you're in the right concept of directions. Okay, if in the MCQs this may help. Next part we see for NH3. Okay, let's see about water because this is one on another extreme, right? So water should have the highest wavelength. So that is 675. That will be like around somewhere over here. So that should actually give like violet. It should give green, right? Because violet is over here, blue is over here, green is over here. So it should give like the last one of these. So it should give green. So water is here, it should give green, and it is at 675. So it is A2x, A2x, C3y. So we can say this is answer, right? Done. Next. MnO4 is deep purple in color, whereas ReO4 is colorless. This is due to great energy required for. Okay, so MnO4 minus is deep purple because of that LMCT, right? And ReO4 is minus is colorless due to in. Okay, so because ReO4 minus actually undergoes like DD transition in ReO compound compared to Mn compound, right? Because so you see over here, DD transition in the Mn compound is not happen, so we can cancel this out. Charge transfer from O to Re compared to O to Mn. So actually this happens to O to Mn, right? So this cancel it out. Charge transfer to O to Mn compared to O to Re. Okay, so actually ReO4 minus actually undergoes your DD transition, for which it actually has no color. So over here it says less energy required for Mn, thus wavelength is more red, and thus we see the complementary color which is violet. Okay. Okay, so next one, aqueous solution of MnH2 whole 6 3 2 plus complex is pale pink in color. The probable reasons for it are. Okay, is pale pink. So we already have said like Mn2 plus, right? It is a D5 complex. So D5, as we said, there is a spin, like spin forbidden. So over here we have an option disallowed transition by spin selection rule. So it's B is right. So we can cancel this and this out. So we have two left. C, it says presence of two T2 transitions. So this is, we have to know some like concepts of Orgel diagram, or like maybe simple degeneracy rules like D5 for D5 high spin 3 4 5. Okay, so we can see that there's no degeneracy over here. So no degeneracy means as to have the A like Mulliken symbol. So A and B is right, right? So if you don't know if there is a possible of three degeneracy, it can be over here, it can be over here, it can be over here. So it can be three states. So it's given by T, 2G or T1G also sometimes. It can be of two, like it can be over here or it can be over here. So it can be by E, simple, right? And among the following, the correct combination of complex and its color is. Okay, so this is a simple one actually. We have to just again see that XO NC rule that we said before and compare that, like it has the highest energy, so it will have the lowest like wavelength absorption and lowest wavelength absorption, and again we have to apply that color chart over here, right? So lowest wavelength absorption will be like maybe over here somewhere, and it will give you some color over here. So as we know it, like Vib Geor, right? So over here we can say like Cl and F. Okay, both of them have like very low. So I don't think these type of questions actually given over here, but F is actually very low in this X column in the, what do you say, wavelength, right? And because wavelength is low, the color will be a bright color over here. So you have to just compare actually. So it says like we can actually say fluorine, chlorine. Okay, sorry for this. Actually, there's a mistake I made. In actually the petrochemical series, it actually starts with iodine, then with bromine, chlorine, fluorine. So the order actually will be Cl, F, NCS, and then Cn. Right. So it means now we can solve it easily because this I'll have. Let me just rub this part out. Yeah. Yeah. So because this will have like highest wavelength, right? Highest. Uh, so this will have the highest energy, so lowest wavelength, and lowest wavelength. It means that it will show a color that is on this side, and this will show a color that is on this side because essentially it goes from 400 to 700. Okay, so Cl will show the color which is to this extreme. Which one is to this extreme? So blue, yellow, orange, red. So this is actually a wrong option given over here. So actually this should be blue, right? And your Cn, which actually has a lower wavelength. Okay, just let me see this part one time. Okay, yeah, I also thought because you can actually not match high and low wavelengths because the color chart actually over here this actually goes in a round fashion. So we have to do it actually carefully. So we can say lambda is lowest over here, lambda is highest over here, right? If it is highest for Cl, this should actually correspond to something like blue on this end. If it is lowest for your what do you say in for Cn, it should actually correspond to something like over here, like maybe yellow. Okay, so I'm going for this. So maybe and they will give you MCQ options. So like using this concept you have to solve. Okay. Next question, MnOH2 whole 6 2 plus has very light pink color. Best reason for it is. Okay, we discussed this before only. The transition of both orbital forbidden, spin forbidden. Correct order of LMCD energies. We also discussed this before. Previously we had the opposite order. Why? Because it was the wavelength we were seeing. Now we are seeing the energies. So energies will have the opposite order than wavelength. Correct order of intensity of DD transition in complexes for 3D transition metal ion M2 plus. Right. Okay, so we have a cis complex, a trans complex, and a normal complex. Okay, so see, normally all these complexes are like maybe spin allowed. They are all Laporte forbidden. Why? Because they are like octahedral complexes, and the less symmetry they have, less symmetry, the better transition. Okay, so normally a cis complex has less symmetry than a trans, and because over here you have Cl as well, but in this we have just the whole complex, so it has a more symmetry. So this won't have like this will be like more forbidden. This will be like less forbidden. This will be least forbidden, right? Because normally in trans you have the things in opposite ends, right? Like LL, but in cis you have like on the same ends. So obviously this is less symmetry than this. Okay, so yeah, that's it. And thank you guys for watching this. I hope you were benefited. And so we solved all the like MCQs that we had from quotation chemistry PYQs, And I hope this will really help you in the upcoming GATE and NET exam. Okay, thank you. And if there was some like discrepancy because of the background noise or some gaps I had, so forgive me for that. But I hope in overall you have benefited from this.